some things in life that are both fun and useful. The study of random walks fits snugly into both camps. I'm a fairly skewed individual, but I reckon we've already had a bit of fun with them. Now let's use them to price some options, which is arguably still fun. First, you might want to know, what is an option? An option is a financial instrument that gives you the right or option to make a trade on a stock or some other thing of interest at a later point in time. It's a formal way of saying, I don't want to or perhaps need to trade that thing right now, but I'll pay a bit of money for the option to trade it in the future. The option is a financial instrument in its own right, and options are traded everywhere. Fun fact, the word Optiver is an amalgamation of Optiver, which is the Dutch expression for options trader. And I can tell you from experience, if you want to trade options, you better be able to price them. So let's price one together. Now, options trading is an incredibly complex and rich area of maths, so I'm going to take lots of shortcuts and make some helpful assumptions. I really just want to showcase the core ideas. To start, imagine a stock worth $100 and consider an option that locks in the right to buy this stock for $105 exactly 10 days from now. Some terminology, this is a call option with strike price K equals 105 and time to maturity T equal to 10 days. What do you think this option is worth? Well, it kind of depends. You're only going to want to use or exercise the option if the stock is above $105 10 days from now. Otherwise, you may as well pay the market price for the stock. So, crucial to identifying the value of this option is some knowledge as to where this stock is going to be 10 days from now. There's clearly a missing ingredient, the volatility of the stock. In short, how much does it move each day? If we have some model for how the stock moves, we can suppose its probability distribution 10 days from now, and we can use that to calculate the fair value of the call option. Now, how much the stock moves each day is not the technical definition of volatility, but let's not get bogged down here. To keep things simple, imagine that you typically observe the stock to move exactly $1 each day, with an equal chance of moving either up or down. We can model this as a random walk. There are 10 days or 10 coin flips. Heads, the stock goes up by $1, and tails, the stock goes down by $1. Again, this is greatly simplified, but now, given the setup, what do you think the option is worth? For example, would you pay $1 for it? Try and make a decision on this before moving on. As is our custom in this series, let's try doing this without bringing in any large machinery. Firstly, for the option to end up in the money, that is, to have some positive value at maturity, the stock needs to end up greater than $105. Now, think back to video 2. You expected to take n squared steps to get from 0 to n on the number line, and that's for the case where you can't go below 0. As such, you expected to take more than 5 squared or 25 days to go from 100 to 105. So this 10-day option is very unlikely to be exercised. I'm already skeptical of parting with my dollar. Let's go deeper. For the stock to end up above $105, you need at least 8 heads from your 10 coin tosses. In fact, here are the only situations when the option expires with some value. Note that when the stock ends up at $106, the call option has a value of $1 because it lets you buy for $105 something that's worth $106. That's a $1 profit, excluding fees, interest rates, and all the other stuff that grown-ups worry about. The same reasoning also explains the other final positive values of the call option. We can use the binomial model to work out each of the probabilities. Finally, the call option can be priced by computing its expected value, simply taking the sum product of these probabilities with the values of the call option in those scenarios. We end up getting that this call option is worth about 8 cents, so you'd better hold on to your dollar, at least for now. Now, how do we make our setup more realistic? Stocks don't move in such a binary way, right? How should they move? Well, in the theory, a traditional but still not perfect assumption is that the log returns of the stock are normally distributed. Let's unpack what this means. The return of the stock is simply the ratio of its price from one moment to the previous moment. To get the log return, we simply take the natural log of the return. For example, if the stock goes from 100 to 102, then the log return is just going to be the log of 1.02. If you paid attention in calculus, and of course you did, then you know that the Taylor expansion of the logarithm looks like this, for values of x that are near 0. And therefore, you can see that when x is small, the log of 1 plus x is pretty close to x. As such, when the stock goes from 100 to 102, the log return is just the log of 1.02. But this is going to be pretty close to 0.02, which is the percentage move from 100 to 102. Therefore, it can help intuitively to think of log returns as being the same as percentage moves. This is not exact, as we used a linear approximation, but for the purposes of this video, it lets us keep moving. So, let's assume that the percentage moves of our stock are normally distributed. And let's go one weaker. Let's assume that the outright moves of our stock are normally distributed. These small assumptions we are making will not conspire too greatly against us over a 10-day time frame. As such, we assume that each day when our stock takes a step, that step is plucked from a normal distribution with a mean of 0, as there is no bias to go up versus down. But what is the standard deviation of this normal distribution? Well, we want to choose our standard deviation so that the expected size of each step is 1. This is in keeping with our earlier random walk. It is crucial to the operation of a happy life that you know that if x is a random normal variable with mean mu and standard deviation sigma, then the expected absolute value of x is sigma times the square root of 2 on pi. Therefore, if we choose sigma to be equal to the square root of pi on 2, we can then expect the size of our step each day to be 1. Now, let's price our option. Actually, here's a good one for you. Now that we've gone from steps of either plus or minus 1 to steps that are plucked from a normal distribution where the expected step size is 1, will the call option go up or down in value? Or will it stay the same? Pause the video and have a little think. The first step here is understanding the probability distribution of the stock price after 10 days. If we denote by xn the step taken on the nth day, then after 10 days we will have moved x, where x is the sum of x1 up to x10. As these are independent normal random variables, I know from first year probability that the sum will be normally distributed, where the mean is still 0 and the standard deviation is square root 10 times the original standard deviation. Thus, the new standard deviation is equal to the square root of 5 pi. Therefore, because we are starting from 100, the probability distribution of our stock after 10 days will just be a normal distribution with a mean of 100 and a standard deviation of square root of 5 pi. Now, to price the call option, we will compute an expected value as before. However, instead of a sum, we need an integral. Specifically, we need to integrate the product of the probability density function with the payoff of the option. Recall that for a normal distribution, the probability density function takes the following form. Now, noting that the payoff of the option is 0 until we get above 105, from which point it increases dollar for dollar, we can compute the value of our option with the following integral. You can actually compute the above integral using substitution and a table of values of the cumulative normal distribution, but I'll skip the process and just tell you that it evaluates to around 20 cents. Although we took some shortcuts, the result is fairly decent. In fact, the Black-Scholes formula, that most well-known and celebrated options pricing tool, when used in place of our method, gives a value close to 21 cents, so we didn't do too bad. Of course, the simple method we used above would start to wither under the lights of more complex scenarios, whereas the Black-Scholes formula will prove to be more robust. It's still not perfect, however, as it is built on a fair few assumptions itself. In fact, some of the research we do at Optiver involves coming up with novel option pricing techniques, ones that can get around some of the drawbacks of the traditional models. As usual, I'm going to leave you with a problem to solve and send in. Consider the same setup as before. The stock is worth $100 and you need to price the 10-day strike $105 call option. However, this time, each day our step is plucked from a uniform distribution. Note that we still want the expected size of each step to be 1. Happy solving!